So I will continue with the cycle here. So you have to put a shaft here because these two turbines are connected with the same shaft. They have the same shaft here. There's a coupling. Okay, you have coupled them together. So this is the general configuration of that is one open feed water, one closed feed water, and one reheater of this cycle. So I will just put the numbers here so that these numbers are random. Okay, you can put any place, but I will start again from the condenser. This one will be 1, and this one will be 2, and then you will have 3, and then 4, and then 5. You have that 5 here. Then so let me go that way. So you will have that 6 here. Then you will have this 7 here. Then I have the outlet of the turbine, which is 8. Okay, now comes the turbine 1. This one is 9. This 9 is same. Okay, this is the same 9 here. So I can just put 9 here, for example, 9. Let me erase that one. So this is the 9 here. Erase this one too, and on the right, 9 value here. 9. And then you have this 10 here. Then 9 goes to 11 here. And then 11 goes to 12 here. Let me see if there is any number left. So yes, of course, this one. So this one will be that 10, 11, 12, and then 13. You will have that 13 here. So yes, all of the points are numbered. So let's draw it. But before drawing, let me identify which points have the same pressure and which one has the different pressure. So actually, I can write it here, so it's not a problem. And let me go back to the table here. So I have one reheater and 10 kilopascal, 15 megapascal, 600 degrees Celsius. It doesn't change. Reheating happens at 4 megapascal and open feed water at 0.5 megapascals. So this one is at 4 megapascals, and the pressure of open feed water heater is at 1.2 megapascals, and you have that 10 kilopascal and the 15,000 kilopascals with 600 degrees Celsius. I will just write the values which have the same pressure here. So I will just start the 1. So the 1 has the same pressure as 8 because these are the heat exchanger. So P1 is same as P8. Okay. Now goes to 2. 2 has the same pressure as 13, and this one has the same pressure as 3. So you will have that P2 same as P3 and the same as P13. Because this is close, that is heat exchanger. Okay. And let me just draw this one here. These are connected. Okay, these are connected here. And then, so comes that 4. 4 has the same pressure as 5. You can see this is one pipeline. 4 and the 5 has the same pressure. 5 and the 6 has the same pressure. 6 and the 7 has the same pressure. So P4 is same as P5. That is same as P6. And that is same as P6 is actually same as P12 because this is mixing chamber. It has the same constant pressure. So that P12 and P12 is same as P7. Okay. This is next one. And you can see that we have 4 isobaric lines. So one is there, and the one is there, and the one is there, and the one is there. 4. So now comes that P9. So P9 is same as P10. Okay. And the P9 is also same as P11. So that, let me see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay, so I have all of the pressure lines here. Okay. So if you identify these pressure lines, it is okay as a beginning step. And also the pumps is the first step to start with. You have the 0 quality here. And for the pump here, you have the 0 quality here. For the pump here, you have the 0 quality here, and etc. Okay, now let's draw it. We'll just start from the pump 1, which compresses from, and I just need to write the pressure values here. P1 is same as P8, it is 10 kilopascal. And the P2 is same as P3, and that is same as P13, which is open feed water pressure, which is 1.2 megapascal. And the P4 is same as P5, that is same as P6. And these are the pressure lines of the So P4 is same as P5, that is same as P12 and the P7. Let me see, P12 and the P7. And the P7 is the maximum pressure, which is 15 megapascal. So this part is that 15 megapascal. Okay. And the P9 is same as P10, and that one is 4 megapascal. Okay, there is a small error here. The pressure value here, it is not 1.2 megapascal, but it is 0.5 megapascals. Because if you go to the table here, at the table value, you will have that 0.5 megapascal, 4 and the 10 kilopascal and the 15 megapascals. Okay, now let's draw it on the TS diagram. So now I will draw it on the TS diagram, but you should remember that we always start with the pump. Pumps are the easiest one, and therefore we start with pumps. Okay, now let's do that. And so the first pump is from 1 to 2. You have the 1 is at 10 kilopascal and the 2 is at 0.5 megapascal. So you can see that 10 kilopascal, 0.5 megapascal, and the 4 and the 15. So I will start from 1, and then it will be isentropic to state 2. This is the first pump. And then comes the second pump, where it is from 3 to 4, and the pressure at 3, it is that 0.5 megapascal, and the 4 is that 15 megapascal. Okay, now let's do that. So you have that 0.5 megapascal and 15 megapascal. And this is the point 4. And then comes that the next pump, which is that 11 to 12, and the 11 is at 4 megapascal, and the 12 is at 15 megapascal. Okay, therefore from 4, this one is the 4 to 15 megapascal. And this is the point 11, and that one is the point 12. And then from point 12, you have the constant pressure, so from the 12 to 6, and then to 7. 7 is the maximum pressure and the maximum temperature, and if I write it, that 7 will be at 600 degrees and 15 megapascal. So you will have that. Here you have the temperature of 600 degrees Celsius, and this part from where you have that from 4 and the 5, and then you have this, that 12 and the 6, all of them are at the same pressure. But anyway, so I will go from 4 to, that is the point 7 here. I will go with the same pressure line here. Okay. This is the same pressure line. And the 7 is boiler. And the 6 is that inlet for the boiler. And I will find the location of the 6 and the 12 and the 5 later. Okay, so then you have the turbine 1. And the turbine 1, that drops the pressure isentropically from 7 to 9. So you have an isentropic drop, and the 9 is at 4 megapascal. So you will have that 7 to 9. Okay. And then from 9 to 10, you have the reheating process. The temperature is increased back to the same value here. You have this reheating process here. Reheating happens at the constant pressure. So you've got back to the state 10 here. And then from state 10, so then go to turbine 2, and that turbine 2 is doing an isentropic work, and it becomes the inlet of the condenser here, which is 8. So just onwards here. And then you will have this cycle here, which is that 8. And then from 8 to 1, you will have this condenser. Okay. So let me correct this parts, and that one, and this one is also isentropic here. Okay, good. So I have found the locations, and then comes the next location here. So these are the extracted point from the turbine, which is at 13 here, and the pressure of the 13 is 0.5 megapascal. So it will be 0.5 megapascal, and I will use a different color here to make everything clear. So this is point 13. And you have that enthalpy, so m dot 13 and enthalpy 13, you have it, and you have that m dot 2 and enthalpy 2, and you have that m dot 3 and enthalpy 3. And as you can notice here is that this one has the highest enthalpy. Okay, the condenser has the lowest, and this one lives in the medium range. Okay, therefore the enthalpy of this one should drop, or the temperature should drop. So therefore you should go, but this one is at open feed water heater, and this one is at constant pressure. So that enthalpy of this one will drop to a value of 3 here. Okay, this one will drop, but the enthalpy of 2 will increase. So it will go again isentropically to 3 here. You will have an increase in enthalpy. So this one will go in that direction. Okay. So the arrow is here wrong, so it's a bit to the right, to the left actually. So this is the next one. So I have done the 1, 2, 3, 4. I don't have the 5, 6, and 5, 6 is not here. 7 is there, 8 is there, 9, 10, 11, 12, 13, and let me find the points which are the 5 and the 6. 5 and the 6 are from the closed feed water heater here. So let me just write it here. I will have this closed feed water heater, and for that closed feed water heater I have the inlet which is at 9. I have m dot and h9, and then you have also m dot 4 h4, and here you have m dot 5 h5, and also you have that m dot 11 h11. Okay, and for this one has the maximum enthalpy. Okay, and this one is the you will have that minimum enthalpy. Okay. This one has the maximum enthalpy, this one has the minimum enthalpy, and when it passes through its energy, and the enthalpy of this one increases from 4 to 5, and this is the first configuration here. Now let's see the second one, which is the mixing chamber here. Enthalpy of 11 is greater than enthalpy of 5, and the enthalpy of 9 is greater than enthalpy of 5, and that one is greater than enthalpy of 4. Now the mixing chamber here, see the comparison of the values here. For the mixing chamber here, you will have that m dot 5 enthalpy at 5. You will have m dot 12 enthalpy at 12, and also m dot 6 enthalpy at 6. And as you can notice that enthalpy of 11 is greater than enthalpy of 5, and the enthalpy of 12, you can see it here, it is greater than enthalpy of 11. Therefore, so you will have that enthalpy of 12 is greater than enthalpy of 11, and that one is also greater than enthalpy of 5. So it means that 5 is in between this range, 4 and the 5, and also 5 is more than the 4. And now comes the 6 here, and for the 6 value here, so what you have is that you have the mixture. So this one comes here and that one comes here, it is mixed, and you have got one outlet. But the location of 6 also, this one is also under question mark, because if this one has more energy, then 6 will have more enthalpy than the 5. If it has much higher energy, and then 6 will be more than the 5. Okay. So this one is that interchangeable. You can put 5 here or 6 here. It is interchangeable here. This is for the cycle that we have got here. You can see that as we have increased the number of the components, and it becomes more and more complex. And this is the most complex one, so I will not draw it, but you can know that. So you have one closed feed water heater, one open feed water, and 2 closed feed water heaters. You have the traps and the deaerators. Okay, this one is a very complex one, and for the solution of this one, and as well as for the TS diagram of this one, you have to use some software. Okay. But otherwise, even this problem can be complicated if the given values or known values are not, that requiring the iterative steps, because it may be possible that you have the known values, but the solution of the problem requires iteration, so trial and error. Therefore, as the complexity of the problem increases, you have to use some software for the drawing of the TS diagram, as well as to find the required enthalpy values. Okay, then comes that combined gas steam power cycle. Okay, what is that? Here we are using the combination of the Brayton cycle and the Rankin cycle. So you have that Brayton cycle, and it is mixed with the Rankin cycle. So what happens in this cycle is that first let's write the Brayton cycle, what we have inside the Brayton cycle. So in Brayton cycle, you have the compressor, and then from that compressor, you have the combustion chamber. And then from that combustion, you have this turbine. And then from that turbine, you have the outlet. So that here what you have is that, let me write the values here. So this one is the compressor also has some inlet. So here you have 1, then the 0.2 and the 0.3, 0.4. So the outlet of the turbine, the 0.4, T4 has a high temperature. Since it has a very high temperature, what we can do is that we can use it. So how we can use it? We can use it by, by adding cycle. So by adding cycle, and this can be that Rankin cycle. But there are different cycles that we can use it here, but this T4 now it will be a heat source for our boiler. Because in the previous cases, if you remember that for this boiler, for example, the heat source is that fossil fuel. But here that for this combination of the gas cycle and the steam cycle, it's also called the combined cycle. Here you have the heat source as the outlet of the turbine here. So if I add another heat exchanger here, say that it goes from the T4, and I will add a heat exchanger here. Okay, and this heat exchanger will allow me, so this one goes in that way, and it will exit at a temperature of 5. And so I will have one more cycle here, and this cycle will start from, let's say, that point. And let me just so this one will be that cycle that I want. So you can say this one is hot, T4 is hot, it will give up its energy to my new cycle. And for my new cycle, I add a new point here, it is 6, and this one is 7. And that 6 and the 7 becomes that boiler. Okay, so inside you have the water. And then from the 7, I will go to the turbine here. And then from that turbine, I will have the condenser here. And then from that condenser, you have the pump here. And then from that pump, you have the boiler here. You can see the direction of it goes in that direction. And the points, if you add it, it will be that 7 is the same as the turbine here. You will have that 8 here, and you will have this 9 here. You can see you have this combination of the cycles. This is called the combined cycle. This one is the top cycle, and this one is the bottom cycle here. You are using the two cycles together, and here you get, so this one, the difference between these two cycles is that here, this is gas turbine, but the turbine that we are using here is that it is that steam turbine. And the temperature of the 4 is more than the temperature of the 6. So if I just write for the cycle here, so you will have that the temperature of the 4 should be greater than the temperature of the 6. Otherwise, you cannot have the heat transfer here. And if it is not 100% efficiency, the temperature of the 5, also it is possible that it will be greater than the temperature of the 7. Because it is not ideal heat exchanger, you will have that heat losses during the process. Okay, this is the how we get the Brayton cycle. And if you want to complete the cycle, what you can do is that you can add one more component here. And this component again will be heat exchanger, and you will have 5 here and the 1 there. Okay, this one to make cycle complete. Cycle closed. actually. So to make the cycle close, I add one more heat exchanger here. That exchanger, so this one allows to T5, drops to T1. So this one allows the temperature of the 5, drops to T1, and the cycle is back to initial values. Okay, then it can start one more time, it can start one more time in this way. And this one is the Rankin cycle. And if you draw it on the TS diagram here, let me draw it on the TS diagram. So this one is temperature. And here we'll have the entropy, and this is what the dome that you are going to have, and we will have these two pressure lines, one's there and the other one's here. Okay, so what you will have is that you will have the, so let's say that this one is a turbine that I am going to have. From that turbine to this part you will have the condenser. From that condenser you'll have this pump. From that pump, you will have the boiler here. If I just add the numbers here, so you can see that pump inlet is at 9, this one is 0.9, and then 0.6 is the pump outlet, this is 0.6, and the boiler is at outlet of the 7, this one is the boiler, and then you have the turbine here, and this one is at 8. Okay. This is the Rankin cycle. Now I'm adding the topping up. It is called that you're topping up the cycle with a new one, which is the Brayton cycle. And for the Brayton cycle, what you will have is that, so you will have the T4. So if you remember the Brayton cycle, it was something like this one. This is the Brayton cycle. And for this Brayton cycle, you have the firstly the compressor stage, which is from 1 to 2, and then from the combustion stage, which is 2 to 3, and then from the turbine you have the 3 to 4, and then from that 4 to 5 you will have it, and from that 5 to 1 you will also have it. Okay, this is the additional part of the cycle to make it complete. Okay, so let me start it. So that 5 should be approximately here. It should be more than the temperature line here. It should be 5 here, and then you will have this Brayton cycle. Okay. So this one is next component. This one is next component here. Okay. And then we'll actually have another one here, which is the compressor stage. So you will have that for the Brayton cycle here. This one is 0.1, and then you have the compressor, which is 0.2, and then combustion, which is 0.3, and then you have this turbine, which is 0.4, and then you have this 5. As you can notice that from this one here, T4 is greater than T6. Similarly, in my chart here, T4 is greater than T6, and the T5 is also greater than T7. Okay, so in reality. But if in an ideal case, you can have the same temperature, similar temperature at outlets. Okay, but for this one, you will have the difference. But what I will do is that to make the cycle complete, I am adding a heat exchanger here, and that heat exchanger will allow me that the cycle is complete. And let me draw it with the dashed lines here. Okay, this is the point 1 here. You can see this is that Rankin cycle together with the Brayton cycle. And for the second part of the cycle here, so you can see that I'm using, if the T4, so that here it is possible that you don't use water. Okay? It is not required that you always have to use water. You can use some, so for this one, so for example, you use some fluid that has okay. For this one, you can use some fluid that has a lower boiling temperature. Okay, so you can use, for example, that some organic fluids for this one that has lower boiling temperature. Therefore, this one allows the boiling process happen here in boiler. That is the another important part of this cycle. So I will solve this problem. So how do we solve the Rankine cycle problems and then finish today's lecture? So let's start. So what values do we know here is that we know I'll go back to the chart here. So the question that I'm trying to solve is this one. So I know the open feed water heater values, and if you have the 10 kilopascal and the 15 megapascal, and open feed water has 1.2 megapascal of pressure with 600 degrees Celsius of peak pressure. So to start to solve any problems, what you will do is that you will just all of the properties here. You have that 1, you have 2, and you have 3, you have 4, you have 5, 6, and 7. Okay. There are 7 points. And what I'm trying to find for any cycle, enthalpy is the first required quantity. Okay, so that enthalpy most important one. Okay, and then I will just write the process for this cycle here. Okay, and this one is 0.7. And comes that pressure, then temperature, entropy, and then enthalpy. So I have need to know one more thing here is that no. Okay, so this one is the pressure, and this one is for the temperature, and this one is for entropy, and this one is for the enthalpy. Okay, now let's start one by one. For the point 1 here, and also let me add one more thing here is that erase it. One more thing is that quality and the enthalpy. Okay, let's say that we are trying to solve it, and always we are using that Gibbs phase rule. And the Gibbs phase rule says that you have to know 2 intensive independent properties. You have to know it to find any third one. Okay. Now let's start from 1. I know the quality at state 1 because it is 0. And I know the pressure at 1 because that pressure at 1, which is the minimum pressure, it is given in the question. Okay, the question says that it is 10 kilopascals. This is the condenser pressure. So you have that pressure, which is 10 kilopascal. So for the state at 1, I can find the enthalpy. Because Gibbs phase rule, 2 properties, it's okay. Now comes that point 2. And for the point 2, what I will need is that I have this one is isentropic. Okay, and for this isentropic relations, you can find the entropy here. So you will have that entropy, which is, so now I will use different color here. So that this one is isentropic, so the S2 is same as S1. This is the first thing that you can do, and the pressure also at point 2 is known, because 1 to 2, which is the pump here, 1 to 2. And the pump sends pressure from 1, which is 10 kilopascal, and 2 is 1200 kilopascals. And here I also know the pressure value, and that pressure value is 1200 kilopascal. So therefore, this part also solved. I can find the enthalpy value. Or that so this one is the first part. For the pumps, what you can do is that the work of the pump is equal to that nu and the P2 minus P1. This is the work of the pump. And this work of the pump is also equal to enthalpy difference. And therefore, I know the pressure point 1 and the pressure point 2. So by using this one, enthalpy at 2 will be equal to enthalpy at 1 plus that nu multiplied with P2 minus P1. And this nu, since it is incompressible, okay, we can take any state. Okay, take state 1. So state 1 means that I know 10 kilopascal and I know x is 0. So state 1 means that pressure is 10 kilopascal and the quality is 0. So you can find that state here. For the second one, okay, then I can find the enthalpy value here. Comes that state 3. State 3 is here. So that this one is also has 0 quality and the pressure is 1200 kilopascal. So here you have that quality has 0 and the pressure is 1200 kilopascal. And therefore I can find the enthalpy value here. Now comes the state 4, and for the state 4, it is again by using this pump relations here. Okay, so that for this one, or use pump work to find enthalpy. You can use this one by looking at the table, or use pump work. And the state 4, it goes from the 3 to 4, which is 15 megapascal, 15,000 kilopascals. And the enthalpy at 4 is same as enthalpy at 3. Okay. This one's enthalpy at 2 is same as enthalpy at 1. And I can also find the enthalpy. Or what you can do is that you can use pump work to find enthalpy at 4. What is pump work? Enthalpy at 4 will be enthalpy at 3 plus the newt at 3, okay, and P4 minus P3. Comes that 0.5, and the 0.5, I know the pressure, which is 15,000 kilopascal, and the temperature at 5, I know it because it is 600 degrees Celsius. It's given in the question, so therefore I can find the enthalpy value here. You can see that all of the values are okay. And now comes that 0.5 and the 0.6 here, this relationship here. And for that relationship here, you can use the isentropic relationship where S6 is same as S5. You have that S6 is same as S5, and also the pressure at 6 is that 1500 kilopascal. Okay, and then you can find the enthalpy value here. And then comes that 7 here, and for that 7, again S7 is same as S5, and the pressure is 10 kilopascal. Okay, and you can find the enthalpy value here. You just use the tables. Okay, for these ones, you just use the table, you look values and find it. You look values and find it. At the end, you can find any property that you want because you will need enthalpy values alone. So that for the cycles, the enthalpy value is enough. For any of it, enthalpy is enough. So for example, I can go for the turbine one, and the turbine value will just write the energy balance for the enthalpy. Again, enthalpy, for example, for the boiler, the Q in boiler with that enthalpy at 5 minus enthalpy at 4. For the turbine here, write the turbine. Okay, so you have one inlet for the turbine, and Y goes in 7 direction, and 1 minus Y goes in 6 direction. We have 1, and the Y goes in that direction, and the 1 minus Y goes in that direction. And therefore, that work of the turbine will be equal to that enthalpy at 1 minus that the Y times enthalpy at, if you go to point here, it is 7, it is 6. We have that 7 here, and you have that 6 here. It will be that Y times enthalpy at 7, and the plus 1 minus Y times enthalpy at 6. And this is for the work of the turbine. Or it goes from that, this one is, or that in, same as out. This one is for the boiler, and this one is for the turbine. Or what we are trying to find is that the work of the pump, and the work of the pumps in all cases, work pump will be that nu delta P. Okay, so that if I work the example as the work of the pump 2, the work of pump 2, it will be that nu times P4 minus P3. Okay. And the P4, I know it. It is 15,000 kilopascal. And the P3, I know it. It is that 1200 kilopascal. And new value, this one, so I've said it, you can take any state because it is incompressible. You can take state first one or the second one. For this one, I can take the state 3 because I know the quality here. It will be easier for me. And I will just, what we'll do is that, so that it will be that new F at state 3. If you look at the state 3, you can see that it is new F because it is 0 quality. Okay. Or what we can do is that you can find open feed water heater values. So if you go back to here, so I have open feed water heater. And for that open feed water heater, you have one inlet from the pump, which is 1 minus Y. This is 6. Let me just write the values here. You have that 6. And then you have this inlet from the condenser, which is 2. And we have the outlet here, which is 3. Okay, so that 6 is extracted from the turbine with 1 minus y coefficient, and the y coefficient you can see travels here to the turbine, to the condenser, then from the pump back to open feed water heater. So everywhere here you have this y fraction, but here you have 1 minus y fraction. So if you write the energy balance, so this one will be 1 minus y fraction, and the 2 will be that y fraction. Okay, and 1 minus y fraction and the y fraction, you will have that 1. So it will be that 1 minus y multiplied with enthalpy at 6 plus that y times enthalpy at 2 will be equal to enthalpy at 3. Okay, and this one will be that Q open feed water, that open feed water heater properties. And by using this one, you can find the value of y. Okay, and if you find the value of the y, and you can replace back to here and find the pump work, turbine work. Okay. Okay. This is for the turbine. For open feed water heater. And for the condenser, you can see this. How do we find it? So let me write just the condenser here. Okay, so condenser, you will have that again, 7 is inlet and 1 is outlet, and here you have y fraction, because that 1 minus y of the mass flow rate, and here we accept that mass flow rate is unit, unit mass flow rate. This one is that unit mass flow rate. Okay, so for this unit mass flow rate, and you will have this condenser inlet, and you will have this condenser outlet, but with y fraction. So you can do that. You have this condenser here, and for this condenser, you have the y fraction here, which is enthalpy at 7. So y at enthalpy at 7, and the outlet is at, so y into enthalpy at 1. So y into enthalpy at 1. And for the condenser also, you have this Q out. Okay, and therefore the Q out value will be equal to that y times enthalpy at 7 minus enthalpy at 1. This is the condenser. So for any of the, how do we know the y value? You know the y value by this open feed water heater here. So you just work out the y value and find it. And this is how do we solve this Rankine cycle with this open feed water heater problems. But as I said, you can see this is just for one additional component. But if you have different additional components here, you don't have reheater here. You have this reheater, closed feed water heater, and the cycle becomes as complex as this one. And for these complex cycles, we always need the software, because pencil and the paper, because sometimes it is possible that the unknown value needs iteration. You just put the unknown value, try it, and the error, and again try it. So for this process, the pencil and the paper is not enough, but you have to use some software to try the values, different values of it, and get the final value. Okay, so for the one here, so this one, where's that? Okay, there will be homework about this one, that you have this homework for this 10%. Okay, there is another application of the Rankine cycle where we have two purposes at the same time, and one is that heat, and the other one is that power. You have heat at the same time, and you have this power at the same time. And this is called cogeneration, or combined heat power cycle. So we are using this one for heating of the households, or it can be that inside the industrial plant or the manufacturing plant, we are requiring this heating process, and that is also that may be also used to process heating as well as district heating. These are the two possible combinations that we can use this cogeneration. The first one is that back pressure plant, and this one is the simpler one. And here you have this boiler, and then you have this turbine, and then you have the condenser here, and then from that condenser you have the pump here, and the back to the boiler again. So what we are doing is that inside the condenser here, you are giving off heat. So this one is Q out. So that you can use this Q out for discrete heating or process heating. So what you will do is that you will make this one as a heat exchanger here, and that for that heat exchanger, so here you have this. So you will give heat to the fluid here. So if it is, for example, cold fluid, at the inlet it will be hot. So for this hot fluid, you can use as a discrete heating of the buildings, or you can use for the process heating if you are requiring some heating inside the facility, for example, for the chemical processes, etc., or manufacturing processes. So this is the one purpose, and this is the simplest one, which is the back pressure plant. And for this one, we don't have any regulation here, and here you got the power, and in this part you have got the heat. So you can see that two at the same time. Okay, so the second one is that extraction plant, and here you can regulate the flow rate, and you will see that how do we regulate it. And here you have the boiler, and then from that boiler you have the turbine here, and from that turbine you have the back to condenser here, and then from that condenser you will have that pump here. Okay, so just before adding the pump, let me just stop at the outlet of the condenser, because I will add the pump later. So what we have here is that what we are doing, we are extracting some pipeline from the turbine, okay, and also you are taking a line from the pipe of the boiler. So you are adding a valve here, this one and that one, you are mixing them together. So it is heat exchanger, and this heat exchanger outlet is there, and for this heat exchanger outlet and for the condenser outlet, and what you are doing is that you are mixing them before entering the boiler. So here you have this mixing chamber, and you have to mix these fluids together before entering the boiler. And so this mixing chamber is constant pressure, this one is constant pressure, and these two has a constant same pressure, but this one has different pressure, this one has different pressure. Therefore I need pumps. So I will need pump here, and I need pump here. So this one will be that pump 1, and this one will be the pump 2. And the outlets of these pumps goes to mixing chamber here, and that one also goes to that mixing chamber here. And this is the general configuration of the extraction plant. And the heat exchanger that I have added here, this one. And this heat exchanger, it is used for the discrete heating, or that it can be that you are using for it for the process heating. Okay, and whatever purpose that you are using this one, at the end it is a part of the cycle. Okay, and it decreases the power of the turbine. And you have the valve here, you can see that valve, you can regulate the flow rate into this heat exchanger. If you want fully so that only heating, you can fully open this valve. If you want only power, you can close the valve here, and you can close this line here, and you will get only power here. So you can see that you can regulate it. So you have that. In this case, you can have that full load, let's say heating. It is an option that you can do it here, or that full load power. Or you can have these partial loads. So you can regulate all of this by valve. And let's draw the TS diagram for this one, and therefore I will just number the points here. And to number the points, I will start with that one, which will be 1, and then 2, and 3, and you will have that 4, and then you will have this 5, and then you have that 6, you have here the 7, and then 8, and then 9. Okay, and now let's write the pressure values. That the pressure at 1 is same as pressure at 5, because it is condenser, and the pressure at 2, which is the pump outlet, it is same as pressure at 9, and the pressure at 3, it is same as pressure at 9, because it is mixing chamber. And then you have that pressure at 3, and that pressure at 3 is same as pressure at 4. Okay. And then pressure at 7, which is the outlet of this valve here, that is same as 6 because it is heat exchanger. The P7 is same as P6, and that is also same as P8 because that is heat exchanger. Okay. If you look at here, 1, 2, 3, 4, 5, 6, 7, 8, 9, all of the pressures are there, and the pressure values are not given. Let's assume that this one is 15 megapascal. No, this should be that. Let me just say that P1 and the P5, which is the condenser, and it states that 10 kilopascal, and the P2 and the P9 and P3 and the P4, that is 15 megapascal, and the maximum temperature is 600 degrees Celsius, and this one is at 3 megapascal. Okay. These are the values that I've just assumed. Okay, it depends on the question. Let's plot it, and as always, we will start with the pumps here. The first pump is from 1 to 2, so I will just add it from 10 kilopascal to 15 megapascal. And this is 15 megapascal. We have the pump 1 here, and that pump pumps from 1 to 2. We'll go to 15 megapascal. And the second pump is from 8 to 9, and the 8 is at 3 megapascal and 9 is at 15 megapascal. So you will have that 3 megapascal here, and you will have this 9, which is that 15 megapascal. So then goes from that 2, go back to here, 2 is there, and then from 2 to 3, and then 3 to 4. So all of them are isobaric, and the 4 is at maximum temperature and the pressure. So that 4 is here. This is the outlet of the boiler, 600 degrees Celsius, and you should go with the same pressure line here. Okay. Okay, this is from that 2 to 4. I've just not added the points here that you can have that 3 here, you can have that 4 here, and the 9 here. So 9 is there, 3 and the 4 is not here, just I will add it later. And then from the 4 to 5, you have the turbine, so it is isentropic, and 5 is the inlet of the condenser. You will have this 4 to 5. Okay, this is the condenser, and I can close the cycle here. Okay, and now comes that at the outlet of the turbine, which is that 6. So I am taking it at some intermediate stage here. So that 6 will be at the pressure of the 3 megapascal. So I use different color here. That 6 is at 3 megapascal, and this one will be at 0.6. Okay, 0.6 and 8 and the 7, they are mixed together. So that 6 and the 7 is mixed to get 8. Okay, so that let's find first what is 7 here. And the 4 to 7, you have the valve. If you remember from that thermodynamics 1 course, the valves are isentropic device, and they are also irreversible. Because if you remember, you had the KL value for the valves, minor loss coefficient. And irreversible means that entropy will increase. And when you go from 4 to 7, entropy increases and the pressure to 3 megapascal. So 4 is there, and then you have the increase in entropy, and then you have this 7. Entropy increases and the pressure drops to 3 megapascal. So irreversible or pressure drop. Okay. This is 7, and this is 6 here, and then you have the 8 here. 7, 6, and 8, they are mixed together, so that you will have this line. Enthalpy of 7 drops, enthalpy of 6 also drops, and you get 8. The 7 and 6 is mixed, and the enthalpy is drop, or the temperatures drop, and you get 8. Okay, you see what you have done here. So 1, 2, and now comes that 3 here. Of that, you have 9, and you have 2, and you have that 3. Now let's assume where the 3 is. 2 is there, and the 9 is there. So this one comes from the turbine. It has more enthalpy, and this one has lower enthalpy. So that 3 will be in between. So because when you mix it, it will be more than that one and less than this one. So you will have that 3 somewhere around here. Okay. And this is the general cycle for this process here. The one final notice is that, so we are using Rankin cycle for waste heat recovery here. And in power plants, we have the waste heat, and to recover that waste heat, we are using different cycles here. You can use that Kalina cycle or Goswami and organic cycle. What is that? So that first, let me say that let's assume that inside your power plant, inside the plant, you have some waste heat. Okay. What you can do is that you can use this waste heat by placing some boiler here. This is the simplest approach. Okay, and this boiler, you will have that phase change, and then it will go to turbine here, and then from that turbine you will go to condenser, and then from that condenser again the pump, again this boiler. This is the simple configuration for the waste heat recovery. But we can use Kalina cycle, Goswami and organic Rankin cycles, and these are all different cycles that use this waste heat. And also another important thing here is that the working fluids. So how do we select the working fluid? So that if I draw the general Rankin cycle here, so to understand why the working fluid is important. So you have the boiler here, and then you have the turbine here, and then you have the condenser and the back to pump, and then from that pump to boiler. So the first thing is that it should not be very low condensing pressure. So inside this condenser, you don't need to have very low pressure, very low P. It is not desirable. Why? Because if you have the very low pressure here, so that environment is at 1 atm. So if you look at our previous examples, the condenser was at 10 kilopascal, but the PATM is 101 kilopascal. So with this pressure difference, it is possible that you will have that air leakage. Okay, and that air leakage is not desirable for this cycle here. Okay, therefore, this very low condensing pressure is not desirable. And the second thing is that you will need that high enthalpy of vaporization for the fluids. So what it means is that, so you have the boiler here. Inside this boiler, you have this boiling process. As the name suggests, the boiling happens. The enthalpy increases. Say that this is 0.1 here, and the 2 and the 3. So the enthalpy increases from 2 to 3. Enthalpy 3. So you should have very high enthalpy increase during this boiling process, because at the end you will use this energy inside the turbine here. So you have that 0.4, and this is desirable for the Rankin cycle to have high enthalpy of vaporization, and also high thermal conductivity here. It's also desirable for the fluids, because for any of the fluid that you are working here, you are that transferring heat, and that heat transfer should be accepted by the fluid, and that acceptance rate is depending on the thermal conductivity of the fluid. Therefore, high thermal conductivity is also required. And the availability of the fluid, it is also good that it should be available, and it should be, so for example, water. It is available everywhere. You can find it, or air. It is available. Most abundant fluids. But if you are using some chemical fluid, and that fluid, if it is not available, at the end it will affect the costs. And non-toxic, again, these are non-toxic. And for the refrigerants, for example, the refrigerants are also working fluids, but some of them are toxic. And the safe maximum pressure, this is also the thing that we want. This now comes inside the boiler, because if you have the boiler here, and this one works at 15 megapascal. For our examples, that the boiler was at 15 megapascal, and this is a very large pressure, and to withstand that high amount of the pressure, the boilers are very large. Okay? And this large amount of the boiler, you have to have it, otherwise this high amount of pressure can explode the system structure. Okay? And therefore, this is the first desirable stuff, that we should have that safe maximum pressure. So that 15 megapascal is okay for water. But if we had another fluid that we can get the same enthalpy of vaporization, same heat transfer values at lower pressures, that's also desirable. Okay. So that, and this is the first thing. And also high critical temperatures, that's also desirable for our process here, because if you remember this diagram here, TS diagram, so this is the critical point that you are having. Okay, if the critical point is lower, something like this one, you have that critical point that is around here. This one is not desirable, because that when you get closer to the critical point, you have the phase change that goes in that way. Here you have this amount of phase change, and here you have this amount of phase change. So when you get closer to this point, that delta H enthalpy change is 0. So for example, inside the boiler, so the enthalpy doesn't change. And this is not good, because you cannot use the energy inside the turbine here, because there's no energy that you are able to use. Okay, therefore, if this critical pressure is higher, so critical points, if it is something like this one, it is desirable because we have now more space for the cycle to work with. So a cycle can work in this space here. And see, this is the space that you can work with this cycle. Okay, so the best one is that water and the air. These are that there is no cost, and there is no that it is not it's non-toxic, it's available everywhere. Okay, and there is also that CO2 storage and the utilization. This is also the result of the fossil fuel. Okay, and we have lots of fossil fuel from the Rankine cycle and as well as from the gas turbine cycles. Okay, this CO2 due to fossil fuels, and they are, that this is a research topic. This is a research, and they are stored underground, and then they are utilized, because the CO2 is dangerous for the environment, so the pollution. And here the main problem here is that storage versus utilization. It may be that we can ask this question. There's something like that: you have the supply and you have the demand. Okay, so what is the demand versus supply? So we can store lots amount of the CO2, but the utilization is the stuff that we are interested in. How can we utilize this CO2? So there are different mechanisms. For example, for microorganisms, they are using this CO2, or the extraction of the hydrocarbons. So they are using the CO2, or they can use some other purposes. For example, you can get the oxygen back from CO2, or that hydrogen with some chemical reactions, that you can get water back from this CO2. Okay, these are the utilizations, but this, again, we have stated it, how much utilization do we have versus storage? This is also another question that is a research topic, and I think these are all that I can say for the Rankin cycle, and with this one I finished the recording. Okay, good luck.